Greetings. Today we're going to learn about dot products. Here's the definition of dot product. It's easy to follow. You should pause this video now and calculate this yourself. I think that would be for the maximum benefit. A dot product, simply we multiply components and then we add them all together. So we get a single number at the end, and that's the dot product. Right now, you should be concerned about why we do this, but at least you know how to do it. There's going to be some homework like this where you simply calculate the dot product. Now we're going to start talking about properties of dot product. Here's a theorem that has a lot of various properties of the dot product. I think let's try to verify the first equality in item C here. And again, you should pause the video and try it yourself before unpausing and continuing. So in order to verify the first equality here, I could write it out and then write it out in component form. So CV, if V has three components, I could write it as CV1, CV2, CV3 dot, and then W1, W2, W3 for the three components of W. And then according to our definition for dot products, we multiply them together component-wise and then add them together. But then we can factor out the C and then get what looks like the result of a dot product. So this is equal to C times V dot W. Next time we're going to learn another kind of product called cross product. So you should not abbreviate the dot product without the dot, right? Because we're going to be learning two types of products. Notice that now by passing to components, we were able to verify this second equality in this theorem. Let's do another exercise. This one is meaningful. Verify E, V dot V. And again, you've seen how to do it. Pause this video if you haven't. So to do this, simply write a component form. And maybe I can think of V's component as A, B, and C. Then this would be A squared plus B squared plus C squared, and then that would be equal to A squared plus B squared plus C squared, quantity square rooted, and then squared. In other words, that's the length of V squared. I know I did switch notation here, but I think this is suggestive of what's going on, so that's why I wanted to do that. Now the second theorem says that if we have two vectors V and W, and then their dot product is also given as the length of V times the length of W times the cosine of the angle in between those two vectors. And I could prove this, but instead let's take this theorem by faith, and then let's continue thinking about what this leads us to. Now, if we have two non-zero vectors that are orthogonal, meaning they're perpendicular, then the angle between them is pi over 2. And we will write it as V perp W. In that case, what is V and W's dot product? V dot W. Again, pause and think for a moment if you need to. V dot W is equal to this. Right? So let's write this out. The length of V times the length of W times cosine of the angle in between them, which is pi over 2 if they're perpendicular, 90 degrees, pi over 2. The cosine of pi over 2 is 0. So because of that, this whole thing is 0. And that immediately we can follow up with this question. Is this vector 2, 4, 1 orthogonal to -3, 1, 2? How would you check that? Are these two vectors that are in space? Imagine for a moment, I have two vectors like this, and they're floating in space. Is the angle that they're making in between them 90 degrees? That's a pretty hard question to answer before today. But right now, you should know how to do this. If you don't, then pause for a moment and think. Right? So what we figure out above is that we can simply calculate the dot product which will give us a number. So this number, you calculate it out, and I won't bother writing out the details. Yeah, multiply them together and add, we get a number to come out, and it's 0. So yes, they are perpendicular. A single number can tell you whether two vectors are perpendicular or not. If I change the last component to 3, then of course it's not going to be 0 because I'm changing it. And so no, these two vectors are not perpendicular. What I want you to conceptually understand is dot product. At the very least, right now, we know that it's useful for testing whether vectors are orthogonal or not. And why do we care? Well, you know, in our human society, a lot of things are made perpendicular to each other. If you look around your room, I'm sure you can find a lot of right angles. Yeah. So in order to find check whether things are right angles, you can use this dot product idea in order to calculate whether things are perpendicular or not. Now let's think about a very useful idea that comes from the dot product. We'll define a projection of a vector. Let me draw a picture. So suppose we have a vector like this. This is v, and then we have another vector called w, and then we're getting this vector dropping a perpendicular from w to the line through v. So if we drop this and get a perpendicular part, then this perpendicular part, sorry, this parallel part to v, this is called the projection of w. So you write w outside, projection of w along v. So in that order. I did not write this incorrectly. We're projecting w onto the line of v. Now, if we want to find the length of project this vector, I ask you, you should pause and now try to work through this exercise yourself. So I'll continue now, of course. The length of this vector, well, we're given that this angle between them is theta. So using, what is this called? Trig. So we see that the length of w times cosine of the angle will give us the length of the part below. And then part B asks us to find a unit vector in the direction of this projection. Well, that's just v in the direction of v, but we want a unit vector. And last time at the end of class, we already discussed this. To get a unit vector in this direction, we can divide by the length of the vector. So v, maybe it's length 3. If we divide by 3, so multiply by a third, then we'll get a unit length vector in that direction. So finally, if we put these things two together, then we would get that the projection of w along v can be given as, well, let's start with the length of the vector, and then we multiply that by the unit vector. So v is in the direction of v, of course, and then this factor scales v down to a unit vector and then multiply it to get it to the length of the right projection. So that could be our formula for the projection. But notice this cosine. So that came up from last page. We can also write this as v times the length of v times the length of w times cosine theta. And by multiplying by v on top, I should also multiply by v, the length of v on the bottom. And I still have a v outside. So don't get confused. This is a vector right here. And then these are numbers. And so that's an entire number. But v, w, and cosine theta, exactly that was what I was going for. That's v dot w from the previous page. And then also below, from part E of the theorem that we verified, the norm of v times the norm of v is equal to v dot itself. So this is our final formula. It looks a little ridiculous at first, of course, but if you think about it, v dot w is not too hard to calculate. V dot v is also not too hard to calculate. And those are going to be two numbers, honest to God numbers. Right? So that's a fraction. So we're simply scaling the vector v by some kind of fraction to get it to be the right length. Let's continue with exercise number 6. And this you should be able to do all by yourself without my help. So again, please pause this video and give that a try. This is a straightforward calculation. Projection of W along V. We get, let me copy the formula above, V dot W divided by V dot V times V. V dot W is 4 times 2 plus 1 times 3 minus 3 times 1. And the bottom is 4 times 4 plus 1 times 1 plus 3 times 3. And then we multiply that by the vector v, 4, 1, negative 3. So we talked about this. This is just a number. 8 over 26, 4, 1, negative 3. Now here is a new idea, but it's pretty similar. It's consistent with what we were just thinking about. Let me draw the same picture again, V and W. And projection of V is right here. This is proj VW. Perp VW, the perpendicular portion, is W minus proj VW. You can directly calculate this, of course, but in terms of picture, that would be this vector right here. This is W, and then add the reverse of this vector. So we go from here, blah, blah. Oh, that's the same as this. And this is perp VW. In other words, perp VW gives us the perpendicular portion, and a projection gives us the parallel portion of W. And notice that these two add up to W, and that's how we define it here. So we can calculate perp VW directly based on this formula. So W is 231. And proj VW we calculated above. Let me simplify that to 4 over 13, 4, 1, negative 3. And then this is some kind of straightforward arithmetic. 10 over 13, 35 over 13, and 25 over 13. It's an ugly looking vector. Well, I mean, let me not be a judge of the prettiness of vectors, but it looks kind of strange. Anyway, that is this vector. How do we know that this is actually perpendicular? Well, we can verify that fact by using what we learned on the previous page. If we want to verify something is perpendicular, then we can take their dot product. So 10 over 13 times, what is V? V is 4, 1, negative 3. 4 plus 35 over 13 times 1 minus 25 over 13 times 3. So here we're taking a dot product of these two vectors. And that's 40, 75, 70. Yeah, that's exactly 0. So that's verified. What we have shown is these weird looking numbers actually give us a vector that is perpendicular to V. So in this way, we decomposed W into two vectors. One is parallel to V, the other is perpendicular to V, and they sum up to W. This will be useful later when we're thinking about movement in space and so forth, as we use these vectors to model real-life situations. As usual, I've included a bonus problem, and I'm not going to talk about the bonus problem right now, but I encourage some of you to think about this. You can prove that the perpendicular, not just in this specific case that we calculated, but in all cases, the perpendicular portion of W along V is indeed perpendicular to v for any vectors in real space. And what would you do? Yeah, write things out in terms of coordinates, in terms of components, and then carry out all these calculations, and you'll see that things just magically, well, not magically, mathematically cancel out, and everything is very beautiful. So that's it for today. Bye.